Good evening, students. Welcome to GD Chemistry classes. My name is Gautam Das. Today, we are going to discuss another very important thing, which is rearrangement of carbocation. Now, I hope that you have already subscribed my channel. If you didn't, uh, please subscribe it. And if you like this video, uh, please press the like button. Anyway, now regarding stability of carbocation, we have already discussed have 3 classes. You can uh, see my other videos. The link will be provided in the description. Now today we are going to discuss the rearrangement of carbocation. Now whenever reaction proceeds via carbocation intermediate, that may be an SN1, that may be an E1, that may be some addition reactions like alkenes with HX and so on and so on. There is always a possibility of rearrangement, provided, this is important, provided that because of the rearrangement, we get a more stable carbocation, more stable than the previous one from where the rearrangement has started or from where the shifting has occurred. So, whenever the reaction occurs via carbocation, whatever be the reaction, if the intermediate is a carbocation intermediate, there is always a possibility of rearrangement because carbocation is quite stable, that is lifetime is quite okay for the rearrangement to occur. There is always possible rearrangement, but provided we get a more stable carbocation because of the rearrangement. Okay. Now this rearrangement or shifting are of actually 4 types. Number 1 is 1,2 hydride shift. Number 2 is, what is 1,2? We will all discuss 1,2 methyl shift, or you may say 1,2 alkyl, that is R shift generally. Number 3 is 1,2 aryl shift, benzene or benzene derivatives, phenyl or phenyl derivatives. Number 4 is, this is different from this other 3, is 1,2 bond shift, which is actually a part of cyclic shift. Now we'll discuss this 4 last. We'll first discuss these 3. Actually, in JEE mains and especially in JEE advanced type of questions, also in NEET type of question, mostly they give some reactions where there will be always rearrangement occurring. Okay. Now, all this type of rearrangement are intramolecular anisotropic 1,2 shift. What do you mean by intramolecular anisotropic 1,2 shift? By intramolecular, we mean that the migrating group, we'll see the example that it will become much more clear to you. The migrating group are never free in the solution, and obviously it is solvent independent. Okay, they never free in the solution, solvent independent. Anisotropic means the migrating group will jump as an anion. That means it will take the bond pair of electron and it will shift. And 1,2 means, 1,2 shift means it will shift, it will go to its immediately adjacent carbon atom. It cannot be 1,3, it cannot be 1,4, it has to be 1,2. Okay, it has to be 1,2. We'll go to the nearest carbon. Okay. Now another important thing is that in some cases there may be 2 consecutive shifts or even 3 consecutive shifts to get the most stable carbocation. Now here you have to keep one thing in mind, which will become more and more clear to you when you do more and more practice. That suppose I am going to 1 to 2 to 3 to 4 carbocation, and suppose this 4 carbocation is the most stable carbocation, most stable one. It is stable than 1, it is stable than 2, it is stable than 3. But suppose by somehow this 3 carbocation is less stable than the 2,1, then obviously this won't occur, because I've started with the discussion that the rearrangement will only occur whenever, because of the rearrangement, we are getting a more stable carbocation. So if this 3 cannot occur, this 4 cannot occur, all the 4 is much more stable than 1 or even 2. But if this 3 is less stable than this, then this process, this step is not possible, then this step is also not possible, isn't it? Then the reaction will stop here, somewhere here. So you have to be very careful of that mind, keeping in mind that because of rearrangement, we must get a more stable carbocation intermediate. Now, if more than one type of group, which is obviously very common, are present in a compound, in a carbocation in this case, then obviously that group will preferentially shift, which will give us to a more stable carbocation. But normally, this you can simply remember, normally the migratory aptitude decreases like this. Hydride for carbocation, obviously, hydride greater than aryl greater than alkyl. Normally, you can simply follow this. Hydride is preferred over to aryl, aryl preferred over to alkyl shift. Now, among aryl, again, if you consider, I'm not going into details of this part because this will discuss in some other classes. But we can simply say, suppose we have one aryl group where one phenyl group is attached to a plus M, another simple phenyl, another phenyl group attached to a minus M. So, because of obvious reasons, then the phenyl group attached to plus M will be preferred over phenyl group without any group, which is again preferred over phenyl group over 2, which contains the minus M group. But among these, again, we may say that phenyl group for this, between this and this, phenyl group plus M greater than just phenyl, and phenyl group minus M. This comes between this hydride and this alkyl. This thing you have to keep in mind. This is very obvious, obviously. Now, if you take some examples, now suppose, let's take some examples. Suppose I've taken this isobutyl carbocation. We will often come across this type of rearrangement in SN1 while doing SN1 and E1 reactions, particularly, also in some addition reactions like HX addition to alkenes and something like that. So in this case, first of all, whether the rearrangement will occur or not. Now, this is a 1 degree carbocation. We have a hydride group, we have a methyl group. Now, we already know the migratory aptitude. Let's just follow the migratory aptitude, then we'll see why that migratory aptitude is true. Okay. Now, we know that hydride shift will be preferred to methyl shift. So, let's do that hydride shift first. 1 to hydride shift, which by some we already know. So, this is a 1 degree carbocation, but 1 to hydration. Now, this will become more Y anisotropic. This H is not jumping as H plus, it is jumping as H minus. It is taking the bond pair of electron along with it and it is jumping to carbon. Now, whenever it is jumping to this carbon containing positive charge, it will neutralize the positive charge, and this carbon atom has lost its electron, so it will become positive. So, what we are getting CH3, we are getting this plus and CH3. What we are having? We are having a 3 degree carbocation, right? Up to this, it's clear. Obviously, I think it's clear. I have to change my this thing. It's not very good. This is the original duster. Anyway, now suppose we already know hydride is preferred. That's why I've done this. No, suppose forget about it. Suppose you don't know. Let's do the other possible shift, which is methyl shift. If we carry out methyl shift, if we carry out this 1,2 methyl shift, then obviously again it is jumping as CH3 minus. That's why anisotropic is jumping as CH3 minus. Again, this will become positive, and this is coming here for neutralizing positive charge. So this will become CH3, CH plus, CH2, CH3. So this is a 2-degree carbocation. So obviously this is more stable than this, but this is much less stable than this 3-degree carbocation, which 9 alpha hydrogen atom, 9 hypercarbon is not possible. So obviously this won't occur. And that's why generalizing we say that hydride is more preferred to aryl, in which in turn is more preferred to methyl shift. So you now already know. So from now on we won't show the different cases. We'll simply show whatever is actually happening, whatever should happen. So now there's a competition, and we have seen that 1,2 hydride shift is giving a more stable carbocation. So obviously in this case rearrangement is occurring. Now let's say another case, which is another very common intermediate will come across in SN1 reaction, even in E1 reaction, is this, which is a neopentyl carbocation. These are very favorites for this NEET and the JEE's exams. Here there is no competition, but this is a 1-degree carbocation. So obviously there will be a shift, because if I shift any one of them, all are same. If I shift any one of them, we'll get, this is CH2, this is CH3, and this will become positive because this is CH3 is jumping with the 1 pair of electron, so this is losing its electron. So we'll because of this rearrangement, which is a 1,2 methyl shift, we'll get a 3-degree carbocation. So obviously this will occur. These are very two common examples, simple examples, but very common examples. Now this duster is better. Anyway, now I'm giving you a few carbocations. You try to see whether the rearrangements are actually possible there or not. If possible, what type of rearrangement will occur. Okay. So suppose one of these is this. Another is this. Another is this. So it's better if you can pause the video and try on your own, and they can carry on. Anyway, that you can do on your own. Now let us take the first one. Let's first take the first one, which is a 2-degree carbocation. Now, if I make a hydride shift from here, we'll take the 1-degree carbocation. So it's less stable. So there is no meaning of doing that. Now, if we do the hydride shift from here to here, that means suppose we are doing like this. This is the original one. Suppose I am doing this hydride shift. This will become positive and this will become CH2. So we will get, because of the hydride shift, that means rearrangement is actually occurring here. But we are doing rearrangement. Whether it actually occur or not, we are not very sure about that. Let's do that first. If it becomes more stable, then we will say that okay, rearrangement is occurring here. Let's first check it. CH plus, CH2, CH3. Now this is 2-degree, obviously 2-degree, but as well as allylic carbocation. Allylic carbocation more stable. highly stable because of resonance effect, along with being 2 degree and so on. So obviously this carbocation, if I say saying this is A, suppose this is B, stability order B is obviously more stable than A because this is allylic as well as 2 degree, isn't it? So obviously rearrangement is occurring here. Let us take this one. This is the let us take the second one and check whether the rearrangement is possible or not. This is a 3 degree carbocation. We already have a 3 degree carbocation. Now, if we make a hydride shift, there is no meaning of making hydride shift from here to here, here or here. Both are identical because then we'll get 1 degree carbocation at the expense of 3 degree carbocation. That's not actually possible. So if I took a hydride shift from here to here, let's see what happens. We'll get this. We'll get this. This is a benzylic carbocation. Now, here there may be some confusion because after all, you are doing this for the first time in class 11 or just gone to class 12. We all know that tertiary, this is already done in one of the earlier videos or one of the earlier classes. You can see the link in the description. Tertiary butyl carbocation is more stable than benzyl carbocation. But that we already mentioned that does not mean all 3 degree carbocation are more stable than benzyl carbocation. In fact, benzyl carbocation is more stable than this. This is also 3 degree, but it has 8 alpha hydrogen atom, 3, 3, 6, 8, and it has 9 alpha hydrogen atom. Even this is less stable than this. So it is almost like this. This is even less stable than this. This we have all discussed in the earlier stability of carbocation video or class, which the link will be provided in the description. You can check it. So obviously we are here talking about this whenever we are saying this thing. So it is benzylic carbocation. It is getting the plus effect exerted by this as well as the plus effect exerted by this group as well as 1 alpha hydrogen atom. So obviously this is more stable. This portion, if I do this thing, or if I suppose make a labeling this as naming this as C and this is D. So stability, what will be the stability order? The stability order of the carbocation will be D greater than C. So obviously the rearrangement will occur here. Rearrangement will occur here, and the product will be, I mean the rearranged carbocation intermediate will be this. Now if it is E1 elimination, then there will be H plus loss from here. We'll get a alkene here, highly stable alkene because of the 6 hyperconjugate structure. Also we have a conjugation with the phenyl group and so on. So if we have substitution, we'll end up with substitution. But this is highly prone to E1 reaction because it will give very good alkene, which is not, you can, whenever the alkene is formed there, it will be not only conjugated but it also has this hyperconjugate structure and so on. So that will discuss whenever we'll do some videos or classes on alkene stability and so on. So here also the rearrangement is possible and the rearrangement is occurring. In the third case I have given, which is just the application of the migratory reactivity, nothing like that. It is a 1 degree carbocation. Now we have all the 3 possible groups, different groups. It is hydride, methyl, phenyl. Now if we make the hydride shift, we will get this, which is not only benzylic but as well as a 3 degree carbocation, highly stable. So obviously the rearrangement will occur here. Next, this is a very common one, a very simple one rather. If I have this, but you will often come across this. Now you can easily say this. There is no competition. Obviously, this will migrate. This is 1 degree, and this migrates. Is getting highly stable. Much stability difference between this. Not only 3 degree, but there are two phenyl rings, two plusar effect from two sides. Then there is a hyperconjugation here from two hyperconjugation. So it's much highly preferred. This thing. Now suppose I give one application. Now before going into this application, now though I will show you the answer, but these are only simple things. But if you join my classes online or offline, if you live in Kolkata, you can opt for offline classes as well as online classes. If you are staying out of Kolkata, then you can join online classes. Then we will discuss much more difficult ones, and so and so. We can discuss a variety of this thing. Now suppose I have given this one. And if I ask you whether the rearrangement is possible or not, that's a very simple thing. But if rearrangement is possible, where rearrangement will occur and what will be the carbocation which will be formed. If you have understood up to this, you should be able to draw on this thing, provided you have seen the earlier carbocation stability, where we have discussed a few other things, few electronic effects which will come into play here. So if you have understood up to this, if you know all this thing, I've seen the video and I already know this, you should pause and try it on your own. Now, one thing we can say that there will be hydride shift occurring, because if we do a hydride shift, this is a 2 degree. If we do a hydride shift, we are getting benzylic on either side. If you do hydride shift, but obviously both cannot occur simultaneously. So which one will actually occur? That's the question. Which one will occur? Actually, they will give this type of question, where not just 2 degree, 3 degree benzylic, you have to also consider the electronic effects of the other things. That's the GOC, whether you have the total GOC in your hand or not, whether you have fully understood the GOC or not. They will actually test you like that. Now, suppose if I am making this hydride shift, suppose I am making this hydride shift, then what we will get? Hydride shift from here to here. If I simply number it, this is obviously not IUPAC numbering, I'm just numbering it. Suppose this is 1, this is 2, this is 3. This is numbering. Suppose I'm making the hydride shift from 1 to 2. So we'll get this. Carbocation. And suppose we are doing this shift, that is 3 to 2, suppose, which is again 1 to shift actually, but I'm making 1 to shift means what? Adjacent carbocation, the hydride or whatever is shifting, it's adjacent carbocation, a symbolic thing, 1 to shift. So I'm making shift from this, according to this diagram, from 3rd carbon to 2nd carbon. This portion will remain intact as usual. This is becoming CH2, this will become CH plus. This. That means according to this diagram, this is 1, this is 2, this is 3, this is 1, this is 2, this is 3. I mean, just numbered it for understanding properly. Now, if I say this is 1 A and this is another one, which is B, and if I ask you which carbocation is more stable, obviously whatever is more stable that carbocation will be formed, and not the other one. Both cannot be formed. Okay. Now the electronic factor will come into play, not just 2 degree, 3 degree, benzylic, allylic, and so on. Now, this phenyl group is attached to OH. Now, we have already discussed this in, I think, in the stability of carbocation, I think, in part level 1. You can check that level 1 or level 2. For OH, whenever we have OH, plus M is greater than minus F. So, it is overall electron releasing group. So, it is stabilizing it. If I consider this one, now CHO is minus I and minus M. So overall it is an electron withdrawing group. So obviously this carbocation is much less stable than this carbocation. Stability order A is much greater than, more stable than B. So obviously this won't be formed, and this will be formed. Now if we do E1 elimination, there will be double bond here. If we do substitution, there will be current substitution. So this is a very important question. This type of question actually comes, but they will test everything, not just 1 degree, 2 degree, benzylic, allylic, which are the common things, but also the electronic factors will come into play. Now, whenever you will be in actual class, online or offline, there will be more applications where more of this, more of your knowledge will be tested, and so and so. Now let's go to the another thing which we have left till now, which is relatively more complicated than whatever we have done so far, but this is also very important for the JEs and the NEET. Very important. This is 1-2 bond shift, or cyclic shift. Now, for these few things, you have to already know stability of the cycloalkanes. We know that 6,5,4,3. If I consider this for cycloalkane for J advanced level, we can say 6,5,7,8, then 4,3. 6 member cycloalkane, 6 member, 5 member, 7 member, 8 member, 4. This is the actual order. For JE main, up to JE mains, need this is okay. For JE advanced, it is better to know this order also. Okay, 6, 5, 7. This can be simply explained from the angle strength theory and so on. 6 member is most stable, we know, because it exists in the chair form where there is no angle strain, because it actually has a chair form. We know the 6 member ring exists in the chair form where it's like this. Where this bond angle is actually 109 degree, 28 minutes, or 109.5 degree, which is actually sp3 tetrahedral bond angle. So there is no angle strain in 6 member ring or cyclohexane. That's why 6 member ring is most stable, and so on. So that's one. This is one fallacy of Beer-Stein theory. According to Beer-Stein theory, 5 member ring is more stable than 6 member ring. The problem with Beer-Stein theory, that in Beer-Stein theory, all the rings have been considered to be planar, but all the rings are not planar, and so on. So 6 member remains in this chair and boat form, but chair form is even more stable than the boat form, much more stable than the boat form. In boat form, there will be some torsional strain, and so on. So there are also some flipping. Anyway, let's come back to our original discussion, which is 1-2 bond shift. These are again of 2 types. 1-2 bond shift. One is ring expansion. A very common type of question, ring expansion, ring contraction. Ring expansion can be are mainly of 2 types you come across, which is 4 to 5 member ring, 4 member to 5 member ring. Five to 6 member ring. 6 to 7 member ring. This is very rare, but mainly this thing. This is very rare. At your level, you may just neglect this thing. Next is ring contraction. if you consider ring contraction, 7 to 6 member ring, 7 member to 6 member ring, highly possible. Now 4 to 3 member ring. Now most of you may think why 4 to 3 member ring will occur. 4 member ring is more stable than 3 member ring. We'll see to that. Why is that? The basics is already done. Why it is occurring? If you see it, the basics is already done in one of the earlier videos or earlier classes where we were discussing stability of Carbocationl. Another thing may occur, but that is very rare. At your level, you can ignore it. 6 to 5 member ring. This is again very rare. Very rare. Mainly 4 to 5 member ring, 5 to 6 member ring contraction, 7 to 6 member ring, and 4 to 3 member ring. Let us see some very common examples. These are obviously, we are talking about intermediates, not these are obviously not the final product. Intermediates we're talking about. Then this will further undergo substitution or elimination. That depends on various other factors, basicity, nucleophilicity, nature of the solvent, and temperature, polarity of the medium, that is nature of the solvent and such. Now, for ring expansion, suppose I've taken this case, which is cyclobutyl methyl carbocata. Now I can simply show you ring expansion like that, but let's see what are the all possibilities which can occur, what are the all shifting or rearrangement which can occur. Okay, and we will also discuss why ring expansion will be preferred to the other possible shift here. Now, one possible thing is that there is a hydrogen obviously here. This is a 1 degree Carbocationl. Now, suppose we are doing this 1 to hydride shift. Suppose then this carbon atom is losing its electron, so it will become positive, and this will become CH3. So we have this. Now this is a 2 degree Carbocationl. There is no doubt about this. This is 1 degree. This is 2 degree Carbocationl. But here the positive charge is on a 4 membered ring, which is highly strained. It's a simple concept of cycloalkanes and whatever. Highly strained, because in order to be sp2 it has to be 120 degree, but here the bond angles are forced to be 90 degrees, so there is high strain. So this actually is not highly feasible. So this will not occur. Okay. Although 2 degree, but positive charge of 4 member ring is not at all stable. It's highly unstable. Now then forget about this, whatever I've shown. I've just shown you what are the possibilities, because this may come to your mind. So why not the hydride shift is occurring? Now, if we do ring expansion, let me show you like this here from here. I'm doing like this. It's always better to number it, to start with, to number it. Then there will be any confusion, because even if I give substituent somewhere, that will be some applications which I will only do in my class. Okay, not in this video, obviously. When there will be a big competition, it's a tougher things. Then it's always very difficult if you don't do the numbering. I'm doing numbering. This carbon atom will be now within the ring. I'm breaking this bond. I'm forming a bond with this. So I'm numbering like this: 1, 2, 3, 4, 5. This is the numbering I follow. You can follow another type of numbering, but just stick to one type of numbering so that you don't get confused. So I'm breaking the 1,3 bond. I'm breaking the bond between 1 and 3, and I'm forming a bond between 1 and 2. So from 4 to I formed a 5 membered ring, and third carbon, this third, according to this diagram, third carbon has lost its electron, so it will be a positive charge. Okay, so we'll get a 5 membered ring. 1, 2, 3, 4, 5, 5 membered ring. There's no problem with that. 1, 2, 3, 4, 5. Now what I've done is that, let's say it once more. I'm breaking the bond. Try to understand very carefully. I'm breaking this bond between 1 and 3. I'm forming a bond between 1 and 2. So this one carbon atom has lost its electron, but this third carbon has lost its electron. So, and this has gained electron. So it is being positive 1, 2, 3. So this will be a positive charge. Now this was originally 1 degree carbocation. This is not only just 2 degree carbocation, but it is also C5. 5-member ring. Strain is much relieved. So this rearrangement is highly possible. This is ring expansion, or also known as 1-2 bond shift. 1-2 ring expansion. This ring expansion nothing but another example of 1-2 bond shift. Now suppose I give you one substituent. If you do the numbering, so numbering will be here, but the shifting may not be like this. So you have to check that. You have to check them that we only do in classes whenever we go to some higher level and so on. So here we're doing the basics. Obviously, at last I will give you one very important and complicated question, and we'll see. We'll see whatever you can actually do on your own. Let's say another example of the ring expansion. Obvious thing. This I think you can do on your own. This is a 5-member ring. Obviously, this hydride shift prefer to hydride shift. If we do the ring expansion, we'll get a 6-member ring, which is more stable than 5-member ring. So if we like this, do like this 1, 2, 3, 4, 5, 6. We are getting 6-member ring. This 2 carbon is now within the ring, and the third carbon, as we have already discussed in details in the earlier one, the third carbon lost its electrons, so the positive charge will be on the third carbon. So this is a 1 degree carbocation. Because of the ring expansion, which is another type of 1-2 bond shift, we will get a 6-member ring. 1, 2, 3, 4, 5, 6. The third carbon is bearing a positive charge. Okay, so we are getting a more stable 1 degree. We are getting a 2 degree carbocation, and also 6-member ring. Okay, so this will also occur. So these are 2 very common examples of. Now this will become difficult, relatively difficult, whenever I give some substituents on the 5-member ring or on the 4-member ring. But that we'll do only in classes. Those who will join classes, my joint classes, they can do that thing. Now let us see another very common example. Very common example. If you see the PIQs of last few years of JEE Mains, you often come across this thing. Suppose in one reaction you have carbon approach this carbocation. There will be ring contraction. Positive charge on the ring actually facilitates ring contraction, provided those things are followed 4 to 5, 7 to 6, or 4 to 3. And positive outside the ring facilitates ring expansion, provided those things are followed, which already exists 5 to 6 or 4 to 5. Now here there will be ring contraction. 1, 2, 3, 4, 5, 6. Suppose I'm labeling this carbon as 1 dash. Okay. So I'm breaking the bond between 1 and 1 dash, and I'm forming a bond between 1 and 2. So first of all, we are getting a 6-member ring. Let's draw the 6-member ring first. Now this CH2, this is obviously CH2. This CH2 will become plus because I'm breaking this bond and forming a bond between 1 and 2. So this CH2 will be plus. Now this CH2 is not attached to 1, it is attached to 2, isn't it? I'm broken this bond. It's attached to 2. So 1, 2, 3, 4, 5, 6 to this 2 carbon, second carbon. This is attached, which is our 1 degree carbocation. Now, this is a very important thing. You have to check whether I can get more stable carbon. Here, again, now here if we do 1-2 hydride shift, it's very important, very important. 2 consecutive shifts. If we do 1-2, one is ring contraction and 1 hydration, we are getting 3 degree as well as 6-member. So this is highly favored. Highly favored. This is very important. Often comes. Isn't often comes. Now, if there is dehydration, E1 elimination, then obviously double bond will be formed here. More hyperconjugation structure, more alpha hydrogen atom, and so on. and if there is simple substitution, the positive charge will be attacked by nucleophile and we will get a simple product. Now let us see this one, which is a cyclobutyl carbocation. Now there comes this confusing thing. It's not confusing if you know the basic fact. If see the earlier videos, it will be clear. Now suppose 4 to 3, I'm doing this thing. So this is no more part of the ring. I'm taking 1, 2, 3. I'm suppose mentioning is 1 dash. So we have a 3-membered ring. This is the 1 dash 1. This H2 has lost its electron positive. This is 1, 2. This is 3. This 1 dash carbon is no more attached to 1 because this bond has been broken. It is attached to 2 carbon. Now here then no further hydride shift will occur. The rearrangement step will stop here. No further rearrangement step. Now it will may undergo substitution, may undergo elimination. That's different thing. But no further rearrangement. No further rearrangement. Here comes the confusing thing. You may say, why not? Because 4-membered ring is, this is a carbocation outside the ring, which facilitates the ring expansion. Moreover, 4-membered ring is more stable than 3-membered ring. So why is not? That we have discussed in details in the stability of carbocation. I think it's in video 2 or video 3. This is CPM, cyclopropyl methyl carbocation, which is highly stable because of something called dancing resonance or sigma bond resonance. If you remember, or if you don't know, you can check that region. The sp5 hybridization. This is even much more stable than benzyl carbocation. This we have discussed. That's why here no further hydride shift like the earlier one, no ring expansion, and this means whenever you have come across this, there will be no further rearrangement, no further shifting. This will then undergo either substitution or elimination as the case may be. So this is our actually the rearrangement of carbocation. Now I just I want to give you one question. Let's just suppose I'm giving you this thing. Suppose I'm giving you this thing. This two are obviously methyl. And I want to see whether if I ask you whether rearrangement actually occurs here. If occurs, what will be the rearrangement product? Can you do it? If you can do it, then you think I think you are ready for the J's. Even for the JE advanced, you are ready. Right? In our classes, we do a lot of these things, even much more complicated than this thing. But let me show you. Since I've shown you, let me show you whether it's actually possible or whether rearrangement is possible. These are 2 methyl groups. Okay, whether rearrangement is actually possible or not. The rearrangement will be occurring here. Why? We're coming to that. It's become a little clumsy. Sorry for that. Now, what we are doing is that there's a positive charge here. I am breaking this bond. I'm expanding this. That means this is a 4-membered ring. I am going for 4 to 5-membered ring. Isn't it? So this carbon has lost its electrons, so the positive charge will be this. What is the another possibility? There's a positive charge on the ring, there may be ring contraction. But 4 to 5 membered, this will be more preferred than 6 to 5 ring contraction. If I do this, and the other possibility is 6 to 5. Now if I see this, numbering it 1, 2, 3, 4, 5. So here this is 4-membered ring, 1, 2, 3, 4, 5. I have formed 1 5-membered ring, and the original 6-membered ring remains as such. Originally, what is it that? Originally there is 1 6-membered ring and there is 1 5-membered ring. Okay. If you do it the three-dimensional one, that will become much more easier. Now we have what we have. Why it is more stable? You may say it, how come it is more stable? It is a 3-degree one, you're getting it to 2-degree one. So how are you saying it is more stable? Now here it's a 3-degree one, no doubt about it. But what if I look at the compound, it's total compound. It's very important. That's all. Very quite big. If you can do this on your own, that means you're well prepared for the J now. If you look at this compound contains 6-membered ring, and this portion. If I just number this portion, this is 1, 2, 3, 4, 6-membered ring, another 4-membered ring. 6-membered is quite evident, so I'm not numbering it. I've expanded that 6-membered ring. I've just make it. Let's also make it this blue. 1, 2, 3, 4, 5. I've expanded to 5-membered ring. So 6, 4 bridge system, and we have another bridge system with 6 and 5-membered ring. You tell me which one is more stable. There's 2 bridge ring system where there is no positive charge on the bridgehead carbocation. So bridgehead carbocation does not exist. We have discussed in some earlier classes. Earlier to stability of carbocation, you can check those videos. The link will be there. But here we have 6 and 4, and here we have 6-membered. We have a bridge compound where I have 2 rings, where one of them is 6 and 5. Hopefully you like the video. So please, if you have liked the video, and if you think that this video has really helped you, please subscribe the channel and press the like button, and so that when I post some videos, you will come to know about it. And it's better if you join my classes, the details of which are given here. If you want to join my classes, leave me a message in this number given in the WhatsApp number, and I will let you know when to call me to join my classes. Okay, thank you. Good night.